Okay, assalamualaikum and good afternoon, everyone. So, I think today we continue with the quantum field theory. So, I'll be speaking still on the same topic of actions and symmetries, but perhaps a little bit more detail today. So, let me share. Yeah, I suppose. Okay, can you see this?
Yes.
Okay, this is essentially no. I was thinking of how am I supposed to continue with from the previous lecture, and then I think in the last lecture or the last talk, essentially we were asking about details. So probably the natural place for me to continue is probably just follows Ramon's what you call book where the subsequent sections that he uh, went through in the book was to look into some of the details of the transformation, the symmetry transformation, and it's still space-time symmetries rather than the internal symmetries. I suppose the internal symmetries will have to be, you have to wait for for some other time. So so let me, how do I do this? So so it's going to be short today because I have not quite finished the slides. But if time permits, I can continue on the whiteboard. Uh, so the introduction is just to recap some of the things, and then and also some ideas that probably haven't been mentioned explicitly last talk.
Wait, Doctor, is someone trying to get in? Tan told me he cannot join. Did you
I think I've set auto admit.
auto admit? Oh, okay, I asked him to try again. Lah. He said cannot. Okay, right. Thank you. Sorry.
Right, where am I? Right. So, and then what we're going to do is to look at some of the transformation of the fields. Okay, essentially, looking at how you build up the action functionals themselves in the end. Okay, the ultimate end is to be able to write down uh, the the right action functional, or more specifically, it would be the Lagrangian density. Okay, so. So we'll be looking at the local scalar fields and then the spinor fields. This is where I had trouble um, typing it up. So we'll probably continue if we want to finish off. Then we'll probably continue on the whiteboard instead. Okay, let me just go to. So recap of the previous talk. So what we did was to introduce action functionals, and remember the action is some way a kind of quantity that sort of uh, since the action is having the same dimension as the Planck constant, so it will come what you call it will play a role in a way that characterize the quantum behavior. More specifically, if you want the natural setting for this, would be the path integral, but no, you wait for some other time to introduce that. And then the symmetries that we are talking about in the previous talk was to talk about the flat space-time, where the symmetries are given by the Poincare group, and then the fields themselves will have to be carrying some kind of some representations of Poincare group. Okay? So these are all from Ramon's field theory book. Okay? And then we also look at the invariance of point-carrier group, and then we find that okay, the fields will be characterized as will be characterized by their masses and spins. So in this particular talk, essentially, we're going to look a bit, extend a little bit beyond point-carrier group. You will see it in a minute, and then we'll try to think of how we build the actions, and the way we build the actions is that going to use Lorentz invariant. I hope everyone's able to come in. Okay. Right. So the next thing is I did mention just now that we're going to slightly go beyond Poincare group the way we have introduced earlier. Particularly, we will find that, okay, spin is going to come in. Okay, so how does it actually get realized from the point of view of space-time symmetries? If you think of the space-time coordinates being just simply R4, okay, and then the inner product will have signature -2, and then the right symmetry group is just your Lorentz group or the special orthogonal group in 3+1 dimensions. Now, this doesn't give you a kind of way of introducing the intrinsic variables of spin, okay? But one could sort of, okay, there's an associated group of SO31, okay? Just like you have SO3, okay, SO3, you can go to the double covering of SO3 to get SE2, and then SE2, you will be able to accommodate spins. It's the same thing here, okay? The fact that SO31 will have also a double cover. Okay? The way to think about it this is to remember your space-time coordinates. Okay? They are now being written in terms of your polymetrics. Okay, the polymetric sigma here, which is the usual definition of polymetrics, and then you append this with the identity metrics, and you are able to sort of represent the space-time coordinates as a matrix. Okay, and this matrix you can easily check that the determinant is just simply your what you call the absolute four-dimensional interval, okay, which is the invariant. So anything, any transformation in this particular case that preserves the determinant of this matrix, this kind of matrix, then will be a symmetry group. Okay? So in this particular case, you find that your symmetry group is given by SL to C. Okay, you can sort of. Is there somebody question?
That's me.
Okay.
That's me. So slightly irrelevant question. Usually, how would you detect, like, for example, a group is a double cover of the other? So you look for that modulo Z2, is it?
Yes, normally there will be a discrete group. So in other words, the way there's no, it involves the center rather. No, you talk about the center of the group, and the center of the group is given by I plus I and minus I, okay, which is actually represented by this Z2 here. So if you mod this thing out, then you get your SO31 back.
So usually one operates on the group level or the algebra level in this case. Like
The algebra, if we think in terms of Lie algebra, then you will miss out this double covering. Just like you cannot really detect the difference between SU2 and SO3 using the Lie algebra because they have the same Lie algebraic relations. So you need to go to the global view. But again, the point is, I mean, the internal variable is still a mysterious kind of thing. Okay, so that's why one of the things that one would like to try to understand a little bit more is why is this double covering, or the internal space thing is actually what does what do they physically mean in a way. So but in any case, okay, mathematically it's just that. Okay, it's just a double covering. So your SL2C will be the double covering of your SO31. And SL2C sort of preserve this metric, and that means your determinant dash will be equal. Okay, and then that sort of gives you the physical contact with the four-dimensional interval invariance. Okay.
Okay, thank you.
Right. Okay. So I suppose I've covered that. This also gives you, if normally general relativity is introduced using the, just the, the four-dimensional space-time thing. But if you want to have a spinorial formulation, okay, we should, one of the things that we are supposed to learn in Cambridge last time from John Stewart. So he has a book, okay, that talks about how do you do, how do you go from the ordinary differential geometry formulation of general relativity to the spinorial one. So you can just look it up, okay. So let me next. Okay. So what we're trying to do is to remember that we want to build up the action functionals, and then the action functionals come from your Lagrangian density, and your Lagrangian density should involve the fields. Okay, so the fields will carry representations of your Poincare group in general, or Lorentz group in particular, and what you need in that particular case, you make combinations of the fields to form Lorentz invariants, so that you can plug it in, and then if you go from one reference frame to another reference frame, then that action or that Lagrangian density still works. Okay, so so now let's try to do this in a little more detail. We look at the idea of infinitesimal transformation. So the infinitesimal transformation sort of connects with the algebra kind of thing. Okay, so you consider an arbitrary function of space-time point. Okay, the function later on you can think of these functions as fields later on, and then in one particular inertial frame, this will this function f, okay, will depend on some coordinate system given by that frame. But in another frame, no, it will be given by a different function, okay, depending on the different coordinates. Okay. So one would be interested to understand how the change of this function is being dictated by the symmetries of the underlying spacetime. So let's do the infinitesimal case. So the coordinate transformation will be transform from x to x dash, okay, and there will be some infinitesimal what you call well, the one that transforms the coordinate. Okay, so here I'm putting this in still in a very general form. One could see later on could be something more specific. Okay, so this delta S mu will be thought as a small quantity. Okay? So that is the space-time coordinate, but then one needs to understand what happens to the fields themselves or the functions themselves. So basically, the change in the function will involve not just the change in coordinates there, but also the change in the form of the functionals that appears. Okay, but then one could start plugging in your x dash in this f dash there, okay, using this. Okay. I hope you can see my pointer here.
Yeah.
Okay, so one can plug x dash into the argument there, and then just like the usual thing, because your added term here is an infinitesimal uh, transformation, then you can actually do a Taylor expansion, and then you can ignore some of the higher order terms. In this case, we just ignore even from the quadratic term onwards. Okay, so we just look at the linear terms. Okay, so what we're gonna get is we're gonna get f dash at evaluated at x, and then you have this sort of parameter that sort of do the transformation, and then you have the derivative of your f dash at x. Okay, so one remembered our main concern here is how the function itself being changed. So the function, one could split up this thing into two parts. Okay, so you can write it in this following way. So there will be a function that I think I've left out fx over here. There will be a yeah, there should be another minus fx here. So one could actually write that as delta not f. So delta not f sort of measures the changes in the functional form. Okay, and then you have the terms that sort of what should I say, that depends on the derivative. Okay, and one can do this in general, and then one can even think of your delta here can be expressed as an operator acting on the function. Okay, and then there will be another operator delta naught that tells you how the function will change. Okay, and then together with the derivative. Okay, now let's consider the yes.
That del mu f is f prime, right?
Which one? If
The delta f. So you have delta naught f plus delta x mu, and then del mu should be f prime, right?
yeah. I think
All right. Okay.
I think I put it. We're going to say something about that. Yeah,
Right.
it should be delta f. Sorry, partial f dash. Okay, and then f dash at the point x. Okay. But if one sort of one can do the calculation. You want to see the calculation kind of thing? Or okay, well, what's going to happen is that instead of d mu f dash, we're going to say that okay, your d mu f dash can be written in terms of a d mu f. Okay, and because there will be some another delta coming out from the d mu f dash. Okay, you will multiply with this delta, so there will be a delta squared term. So in other words, one can ignore the part of the delta squared and just assume this to be d mu f.
So just briefly, is it something like a chain rule? Do I understand it correctly? Like,
Well, not quite. It's just you just ignore the delta squared term.
okay, never mind.
Okay, I mean,
just
you just need to go to the details. So essentially, you just re-express things back to the, whatever definition that we have, and then you find that this term already has a delta x mu, and then by replacing your f dash with f plus something else, that something else also has another delta. So when it multiplies with this delta in front here, so you get a delta square. Okay, all right. If you want to see the details, I can show you later on, I suppose. Now, okay. Now let's look at a simple case where you just have translation. Now, one needs to understand what does it do. Okay, what does it do to the case of the functions? Now, generally, when you translate your coordinates, okay, there will be some changes to your function. But you have to remember now, your f is going to be representing a physical, what you call, thing, okay? A physical thing. And a physical thing, normally you formulate a physical, say, absorber in a way that you do not want that observable or that function, okay, to be dependent on the origin, right? So you formulate in such a way that it's actually, you know, no matter how you do the what you call translations of the origin, no, it will, no, it still represent the same thing. Can you take that?
Come again, Doctor? What is the...
Okay, the point is you do not want to have a physical quantity depending on the choice of your origin to make it a good physical function.
So this is the proper physical function?
That would be, if it depends on the physical, if the physical
origin.
function depends on the origin of the coordinate, then it's not quite a good function itself.
Okay, so if this not depends on origin, they are, what do we... So
meaning you can now simply use any coordinate systems, okay? We just no, you just translate your origin anywhere, and it's still being given by the same function.
So then we have the invariant.
Well, okay, it's not quite. I mean, if you would think in terms of, I suppose translation invariant, I suppose if you want to put in terms of that.
Okay.
But in other words, you do not want it to
Dependent on origin.
to be dependent on where the origin is.
Okay.
So in this case, when you translate, okay, you always translate the origin. Okay, so in that case, one would expect the fields in this particular case, usually if we think of fields as being physical, will have no change in the form itself under translation. Okay, so in that particular case, then what will happen in this case, then your delta f over here will be 0. And then you'll be able to get your functional change, your delta naught f, since this is 0, in terms of this infinitesimal transformation. So for the case of the translation, will be given by the derivative of your function, okay, which is the derivative. Okay, this is sort of going ahead and thinking in terms of your quantum theory. Then your derivative is actually your momentum operator. Okay.
Doctor, so for the var epsilon mu, that will be the infinitesimal change.
Which one are you referring to?
Var epsilon mu.
For
epsilon.
Okay, your epsilon mu is okay. I've made the changes. Remember that this is supposed to be small. Now I'm replacing your delta x mu by your epsilon mu. That means it's just an infinitesimal translation.
Infinitesimal translation.
Okay. So in this case, will be an infinitesimal transformation, which is can be general. Okay, but now here you're just doing the make a infinitesimal translation, so it's just like a small distance change. Okay. I hope that sounds okay. So with respect to the translation, you expect that okay, you're not really interested how the functional change is going to be, because your fields are going to be physical, and you do not want it to depend on that changes. Okay. Now let's move on to the next, what you call, okay, how should I say it? At the previous slide, we are just considering translation. Oops. Okay, we are just considering translations, but you have to remember when we talk about inertial frames, you can do other things as well besides translation. Okay, you can do rotations. Okay, so the rotation part is going to be the one that sort of complicates things. Okay, so let's look at the next simplest case to think about is the scalar fields. Okay, so by definition, your scalar fields are just functions that does not change under change of coordinates. Okay, so in other words, your phi dash x dash will be just the same as phi x. Okay, so in that particular case, you know directly from that assertion that your delta phi is going to be 0, and then you can now simply get your delta naught, the functional change. Okay, so in this particular case, now we are now considering other things, other transformations besides translation. So in this case, there will be rotation. Okay, which is just sort of mixing the spatial coordinates, but you also can do boost transformation, for which your time and space can also be rotated between each other. Okay, so one has, for example, the change in the coordinates now will be given by some generator here, which is given previously as your angular momentum generator. Okay, I can remember. Okay, your angular momentum generator will have your angular momentum as well as the boost. Okay, and there will be some parameters. Okay, so and you can check that, I think, from the previous what you call talk. No, this will have to be obey certain algebras and so on and so forth. So now one could now think of, okay, your scalars, since your coordinates will transform in this way, your scalars will also depend on that generator thing. Okay, so in other words, the functional change with respect to the scalar field can be determined by this generator thing. Okay, but scalar fields are not the only thing that we will consider when you build up your action functional. Okay, because you would also need some derivatives. Okay, you remember the Klein-Gordon equation, for example. Then you will find that, okay, there will be a term which is d mu phi. Okay, so we need to consider the ingredient is still scalar fields, but you need to consider the derivatives of your scalar field. So the derivative of the scalar field will have again the infinitesimal transformation, which we can write it as using this. Remember that this is just like your operators thing. So now here you just sort of shuffle your transformation with the derivative. Okay, so you use a commutator there, and then you can have just your derivative of the transformation. Okay, So putting all these things together, then you probably need to understand what this commutator is. Okay. So over here, okay, I'm mixing. I've forgotten a backslash new there. Okay. So this is partial. Okay. Can I actually sketch on this? Okay. This one, okay, probably not because I have only the Acrobat. So this is partial new. Okay. Forgot the backslash there. So you have your epsilon new rho x rho partial new partial mu. And where this that come from is coming from here. Okay, remember your this part, okay, can be written as that. And now you might want to ask, where does it come from? Well, you go back to the algebra of your m's. Okay. So again, what about this one? Okay. Well, in this particular case, the fact that your partial mu is just like your translation, okay, the generator of translation. So this will be 0. So the only term that you need to be concerned with is this part. Okay. So you work out this commutator, and then you'll be able to get this answer because you have the derivative here, and then you have your x here coming from that transformation there, and then you'll be able to write it in this particular. Okay. So if you put all those things together, then your m mu nu, m rho sigma here, if you remember, can be written in terms of two parts: the generalized angular momentum, which is coming from the rotational part, and also the spin part. The spin part is going to be the one that sort of gives you a little bit, complicates things a little bit. Okay, so you have this, the angular part, and then you have the spin part. And over here, the spin part actually is sort of, what does it actually do? It sort of juggles the indices somehow. Okay. So it's given by that part here is given by this. So here you really need to do the, it's coming from the algebra itself. Okay. So putting everything in, then what one finds is that your as what you call it, as you expect that this derivative of scalar field will transform like a vector field. Okay. Okay. I think now we have to go to the spinor setting. So this part probably I may have to go to the whiteboard. Okay, remember our spinors is coming from, remember the way we sort of characterize the fields last time, the representation of the Poincare group. So what you do, you have your J and K, and then you sort of combine J and K. J is your generators of angular momentum, K will be generators of your boost. You combine in such a way that you can get your SU2 cross SU2 algebra. Okay, but then you find that, okay, that generators of the SU2 algebra is actually no, they are not Hermitian generators. Okay. So, and then you can use the SU2 algebra to give you the two different sort of what you call the quantum numbers. Okay. So, and we claimed before that there are two types of spinors that you can actually see. It's coming from half zero Remember previously was nm there, so that you can have n equals to half, m equals 0, and also the other way. One of them will be corresponding to, sorry, I did this everything this morning, so that is supposed to be complex. Okay, so there will be a left-handed spinner and your right-handed spinner. Okay, so they will transform under Lorentz transformation as well. Okay, but the way that this Lorentz transformation comes in will be from a complex 2x2 matrices. So this makes the connection of the SL to C that we see on it. Okay. Oh, sorry. We okay. So if it's just merely talking about rotations, okay, then you know how the polymatrices can generate the rotations uh, of the fields, just like when we do quantum mechanics last time. Okay, so you can use the spin generator to actually make rotational transformation. Okay, so there's no problem with respect to that. So
sorry, I maybe missed this. LR, like your 11, right?
yeah, okay. That here I'm okay. So
Why?
swap them around. Okay, so I'm just trying to be.
Reading it.
I mean,
Anything.
it's no. It's just saying that okay, there are two lambdas. One is L, one is okay.
Oh, okay.
So
Alright.
at this stage, we don't see any difference between the two. But here, as I said, this correspond only to the rotational part of the Poincare group. Okay.
You mean over here, L left and right equal, is it? And the same.
If you just consider the case of just rotation,
Rotations.
so you just have that. Okay. But one really needs to remember that in your Poincare group, you also have boost transformation. So your boost transformation will also need to be generated by your polymetrics. So the question is how? Well, I mean, I'm not sure how the derivation is made, but you can check because I didn't go to the original literature. But you can check. Okay, okay, this is a thing that we had earlier. Okay, so this will be your rotation. This will be your boost, right? And you can check by defining your K as follows. Okay, with the negative I over 2 there. This will, I did just to make sure that if somebody asked me today, I have I've worked out those. So you can check that it reproduces the right algebra for J and K. You remember the J and K here. Maybe I go to the whiteboard now. Oops. So remember the J and K, you have J, I, J, J. This gives you the simply your rotational thing. But now you have your, I should do the Ki first. Ki, Kj, okay. This will give you some, I'm not mistaken, let me just check. There's a minus, I think. Yeah. There's a minus I epsilon ijk jk. So you can see that, okay, your k does not quite close like your j's. And then with respect to your combination between the two is given by this. So somehow your K and J doesn't quite sort of form a separate algebra altogether. So they are intertwined. Okay. So now all you need to do now, given that your definition earlier, let me just check what did I write down. K equals to minus I on 2 sigma. Oops, sorry. Oh dear. Where do I go? I'm still not very familiar with this. Okay. Okay, you can simply use this into your computation, and then you will find that you get the same algebra back. Okay. So let me go back to the slides. I think we're near the end. So in this case, can check the algebras, and then the way we show that there is a difference between the left-handed and the right-handed is the way how your boost parameter and your rotational parameter being combined with each other. Okay. So in the case of the the left-handed one, you have omega minus I nu. Nu will be your boost generator. Sorry, boost. I should be careful. Here is boost parameters. Okay, boost parameters, and then for the right-handed one will be plus I. Okay. I think probably this will be my last slide there. Yeah. So right now I have to go to the whiteboard. If you, or do you want to stop now and continue with spinners later on, because there's quite a bit.
Oh, okay. Since John going to stop, we have 15, more or less 15 minutes.
I mean,
Yeah, I
if
think-
others still want to join, I think it's fine. But I need to quit at one.
Okay.
So, maybe we can stop, but I have questions.
Okay, go on. So probably we have to continue. So there will be a part 3.
Part 3, okay.
uh,
I have questions. Last slide. Okay, so maybe just we go for question and Q&A.
okay, sure.
Okay, this is interesting. So later maybe you can tunjuk. So this one, lambda, so uppercase lambda L, no, your last slide. Uppercase lambda L.
Which one? Last slide.
Last slide.
Last slide is this.
Yeah. So the relationship between uppercase lambda L and R, so inverse is equal to diagonal?
Okay, maybe I go to the whiteboard now.
Okay. This one is interesting.
So let me just write down, if I can find where it is. Yeah, okay. How do I erase this? How do take that? And then what do I do? So maybe this, and then yeah, take the lasso that.
No, I think it's the one.
No, you kena erase later. You kena eraser. Oh, boleh?
Boleh.
Okay.
Oh. Oh, ini apa ni? Ini whiteboard apa ni? Oh, Microsoft whiteboard.
Okay, so now let me rewrite your lambdas again. So remember that, okay, I have to change that. Tak pandai pakai begini. So your lambda left is now given by this exponential. In some ways, you have an intuition of what's going on. Sorry about this. Sigma, I want the polymetrics. and then they generate your rotations here, and the part that sort of make things a little okay. That would be minus. Sorry. Um, so if we look at this, for example, this becomes like this. Like if you think of this is Hermitian, okay, but here it seems to involve a complex parameter. Okay, so and then what is this thing? Is actually one of them is sort of showing you where the axis of rotation. And then the other one is actually telling you the motion of the code, well, the motion of the, well, in this case, if you think of particle, then the motion of particle, okay, because you boost, okay. So, and then your right, oops, not very too sensitive. The R E I over 2 sigma dot omega plus I u. Right. So the only difference there is essentially in this sign there. Now let us think of what lambda inverse is. Will be E minus I over 2 sigma, so I'm doing this right, dot, I need to cancel the real part, so that gives you omega plus. Or maybe I just work backwards. Lambda R dagger. So that will give you exponential I with 2 sigma dagger. And then your omega will be
minus I mu.
minus it.
Mm.
Okay. So I made a mistake here then. If you want to multiply this with this, you're supposed to get an identity. The first part is no problem. The one that's going to be causing problem is the one with the imaginary. So I think this is probably will be just the minus. Let me erase that. Oh, making it.
Oh, so nanti dia akan equal.
Okay. So this I think will be minus. Hopefully you can. I hope you can check this out. Okay. When you multiply lambda L inverse with lambda L, it's supposed to give you an identity, right?
Identity.
And then you find that okay, this will be the same as lambda R dagger. Sigma dagger is just the same as sigma. Okay. So since that, is that the question that you're asking?
Yes, betul. Do they call it something like with having properties like bi-orthogonal?
Okay, I do not know much about that. There might be some relation, but I don't, what's bi-orthogonal?
Because last time when I did this NCQM, the relationship between the matrices with the commutative polynomials and the deformed polynomials, we have this bi-orthogonality, having this like inverse with dagger, but maybe.
But there, you're talking about SU2s, right?
Yes.
So here, probably there will be some analogous idea, but no.
Okay, okay. All right. Thank you.
Because
That's all.
okay, in some ways there might be some relationship, because here you are thinking of your left-handedness and right-handedness coming
Mm.
from the SE2 as well. Okay, so there might
Okay.
be some relation there.
Okay. Thank you.
So the other thing that I'm supposed to tell you is that because of this relationship between the lambda L and lambda R, you can actually do a kind of conversion that says that, okay, given a left-handed spinner, you can sort of make it look like a right-handed spinner by multiplying your sigma 2 or something like that. Okay, but I think probably I don't want to go into that. Okay, so I will stop there. Or do you have any more questions?
So if I understand it correctly, the omega and mu are just vectors of numbers, right? It's not
Yeah,
like a
they are parameters,
correct.
but complex parameters because of this problem. Even later
Wait,
on,
wait, wait, doctor. They call it complex parameters,
yeah, because you have an I here. Yeah.
but but nu itself can be. Oh, you call nu the complex parameters,
No,
or
no, no.
I?
The because of the I here. Okay.
Oh,
The new is just like is a
uh,
real parameter. Okay.
real parameter. Okay, okay.
So that would be probably no the things to come, I suppose. Let me go to the Ramones there. So there are things like going from all this kind of spinner thing, and then you build up combinations of spinners. Okay, remember previously we had uh, the direct sum of half zero and zero half will transform like a vector. So you can show all of those. Okay? I think somebody asked me the question previously, right? And then you also, if you go to no, these are what we call the if I'm not mistaken, these are what they call Y spinners. And then you form from this Y spinners, you can form the direct spinners, which is the four-dimensional thing. Okay, and then later on, once you have the four-dimensional thing, then you have this idea of a projection operator that involves gamma phi, which I told you, that talks to you about the chirality thing. So probably I should stop now unless you have more questions. So it is pretty no again there are already hints of quantum parts when we talk about the generator and things, because generator of translation is momentum, whether it's quantum or classical. So you have hints of where you're gonna get. But the real point later on when I talk about quantum field theory, just to give you a flavor of what's going on, is that your fields will now be operators instead of just functions. So that's how they and then you associate all the annihilation and creation operators to go along with that. Okay.
Okay, doctor, you have to stop recordings.
Okay, I'll stop recording. Where am I supposed to do that? Okay.